Good afternoon. Today we're going to be looking into the remainder of the course material and just sort of start things off. Okay, last time we had looked into systems of equations and for what we have with systems of equations, again, we have like linear, nonlinear, but let's say that within the official classification of what we have for systems of equations, there will be three particular types, okay, to look at, okay, and the ones we've been looking at have fallen in the category of those that are consistent and independent. Okay, so for what we have for those systems, again, which we have to be consistent and independent. Those systems will have a finite number of solutions. Okay, that is a limited number of solutions. Another classification is going to be with what we have as an inconsistent system. And for this type of system, there will be no solution. And then we have with the third and remaining type of classification, we're going to have those that will be consistent and dependent. And this type of equation system, okay, this is going to have an infinite number of solutions. And to illustrate, okay, what we have for the possible classifications, okay, say if we were to determine the type of system for the following. Or say if we were to determine the classification of each system. And we'll say that we have in the first case, right, say if we have a couple of linear equations in x and y. We'll say that we have x plus y is equal to 7. And we'll say that we have negative x minus y is equal to 10. All right. So here we have equations in x and y, and we're trying to find those values of x and y such that the sum will be 7 and where the difference of their negatives will come out to 10. Okay, so here we have additive inverses, and it turns out we have in both the variables x and y. Okay, so I can add the equations together. So we have x plus y is equal to 7, and we have negative x minus y equals 10. And if we combine, okay, what we have in x and y. So if you notice, you have x's will go out. Also going to have the y terms will go out. And guess what? The whole left-hand side of the equation is going to be 0. But for what we have to the right, we got 7 plus 10 is going to be 17. And guess what? To say that there are going to be any solutions for x and y that will fit to both of these equations amounts to trying to say that 0 is equal to 17. Okay, so we have a false statement for the resulting equality statement. So we're going to have no solution in consequence. And for the type of system we have which has no solution, that is going to be inconsistent. Right, so again, inconsistent system has no solution. Now, I say that if we have another system, and we'll say here that we've got x plus y is equal to 7. So we'll have that introductory equation again. So we have x plus y is equal to 7, and we have x minus y is equal to 1. Okay, so you have a linear system of equations, and this time we have additive inverses only in the variable y. Okay, so you have x plus y is equal to 7. And x minus y is equal to 1. And if we apply the addition method, okay, we'll have only the y terms to cancel. Okay, so adding the equations. Okay, so we'll have x plus x is 2x. And we have that 2x is equal to 8. And we're going to have that x is equal to 4. So we have that x is equal to 4. And if we look at solving for y, again, I can plug in 4 for x into either equation. Now I'll just plug in for x in the first. Okay, so we got x plus y is equal to 7. And again, we have that x is equal to 4. So we have that 4 plus y is equal to 7, and from this we have that y is equal to 3. Okay, so x is at 4, y is at 3. 4 plus 3 is 7. Also 4 minus 3 is equal to 1. Okay, so we have for the solution, again, we have just itemizing what we have for x and y. We had that y is at 3 while x is at 4. And you can write this in ordered pair terms. And since we have just one solution, that is a limited number of solutions, the type of system we have is going to be consistent and independent. Okay, and now another scenario. Okay, say if we have where we don't have additive inverses in either x or y, but still being able to set up a system of linear equations. Let's say we have x plus 2y is equal to 7. And say for the other equation we have negative 2x minus 4y is equal to negative 14. Okay. And for what we have in this case, all right, we have two equations, okay, and we don't have additive inverses in x or y, but I can make an adjustment where we can form the presence of additive inverses. Okay, and you can either cancel out the x terms to solve for y or vice versa. And let's say that if we work with x, okay, so you have x and negative 2x. Now, if I were to cancel out the x terms, I can take the additive inverse of negative 2x with 2x. So to raise the x that I have from the first equation to 2x, I'm going to be looking at doubling all of the first equation. And upon doing so, we have in doubling the first equation, so this will become 2x plus 4y is equal to 14. And again, just leaving the second equation as it is, so negative 2x minus 4y is equal to negative 14. And so for what we have here, now the goal, okay, initially was to get the x terms out, okay, but it just so happens that by doubling the equation I end up with additive inverses for both x and y. And this time, okay, this is still going to work out. You'll have your x terms and the y terms to cancel, and guess what, the constants on the right with 14 and negative 14, they will also cancel. Now before, we had that 0 is equal to 17, and so we wound up with an inconsistent system in the first case. But with 0 equal to 0, okay, that's a true equality statement. And this is going to consist of an infinite number of solutions. And let me mention, okay, so you're going to have for x, okay, if you have a true equality statement, it kind of goes back to the days from the early stages when we had like our types of equations like consistent, inconsistent, and identity. And this is like the system form of an identity, okay, where you're going to have an infinite number of solutions. And for what you're going to have in the case of x, the solution of this is going to be the set of all real numbers. Okay, and especially like in the case of Alex, okay, for all real numbers, you're going to put in terms of what we have for x. But for y, now while the range will also be the set of all real numbers, Alex is particular about how to express y, and that is to express it in terms of x. So for what we have in this case, right, so you have x plus 2y is equal to 7, and putting y in terms of x. Okay, so if I isolate the y term, okay, so you have taking x away, okay, so you have that 2y is equal to x plus 7, and if I divide by 2, we'll have that y is equal to negative x plus 7 all over 2, or negative 1/2 of x plus 7/2. And so for what we have in the case of the outcome, So we'll have in the case of the solution. Okay, so you have for x at the set of all real numbers. And if they're my choosing, I would say that for y had the set of all real numbers. But in case of Alex, it wants that y to be expressed in terms of x. We have that y is equal to negative x plus 7 all over 2, and you have that running throughout the whole real number system. And so for the type of system that we have, again, we have an infinite number of solutions, and this system is going to be consistent and dependent. Alright, so I just want to mention this, okay, for what we have with the classifications of systems of equations. Alright, now just looking into the portions of what we have, and again I had given out 2 subsequent study guides, okay, and the first of the subsequent, okay, was attached to the part 1 study guide, and just reverting to what we have. It's going back to exponential and logarithmic equations and properties, and we have at the start, okay, so we have in the first problem, okay, so you have 8 to the x plus 2 is equal to 4 raised to the 2x. And this is a case of what we have for an exponential equation that is going to share a common base. Again, the number that can multiply itself into both 4 and 8. Okay, it's going to be the number 2. So we've got the common base at 2, so rewriting both 8 and 4 in terms of the exponential base 2. So we have that 8 is going to be 2 to the 3rd. And so 8 to the x plus 2 is going to be 2 cubed to the x plus 2. For 4 raised to the 2x, okay, so 4 is going to be 2 squared to the 2x. And here we have reverting to the power property of exponents. Okay, so for base to a power, raised yet to another power, again, we're going to take the product of the exponents. Okay, so for what we have on the left, okay, so we're going to have 2 raised to the 3x plus 6. It's going to be equal to 2 raised to the 4x. Okay, now we have single terms in base 2. Okay, we've taken care of the power property, and we've individualized our exponents. Okay, so we've got 3x plus 6 on the left, 4x to the right. And I can set these powers equal to each other and solve for x. So we have that 3x plus 6 is equal to 4x, and with 4x by itself on the right, okay, I can just move the 3x over, and taking 3x away. Alright, so we have that 6 equals 4x minus 3x is x, and so just writing in terms of x equals to x on the left hand side, okay, we have declaring that the solution to what we have for 8 to the x plus 2 is equal to 4 raised to the 2x, okay, we'll have that value to end up at 6. Alright, now for what we have in the case of the next item, okay, and and also with the third item. Okay, we have logarithmic equations. And for what we have in number 2, okay, so you have base 2 logarithm of the quantity of x plus 1, and you're going to have plus the base 2 logarithm of the quantity of x plus 3. And I would just mention, okay, for what we have with x plus 1, x plus 3, and also with, I guess you can say with what's going to be leading to the third problem is have 2x minus 7 and the natural logarithm of x. All the attachments that we have must be positive. Okay, so just setting things up while we have beforehand. Okay, so we have with number 2. Okay, so again we had base 2 logarithmic terms. Okay, so I had the base 2 logarithm of the quantity of x plus 1 plus the base 2 logarithm of x plus 3 is equal to 3. And for what I have in this second problem, I want to translate the addition of logarithms into a single base 2 logarithm. Okay, so for the addition and the subtraction properties, again, we will have addition and multiplication to imply each other, transitioning between expanding and combining. And we have also at the other end, we have division and subtraction referring to each other. And now looking at compiling as a single base 2 logarithm. Okay, so I got addition. So this means that x plus 1 and x plus 3 will be multiplying each other. So just looking at combining. So base 2 logarithm, so we have x plus 1 times x plus 3. Again, we have is equal to 3. And if I go ahead and FOIL out, okay, so we'll have the base 2 logarithm. This is going to be of x squared. We got 3x plus x will make 4x. We have plus 3. And we have is equal to 3. And again, we got the separate logarithmic terms into a combined base 2 logarithm. And what I can do now is that I can free up the variable expression from the attachment of a base 2 logarithm by treating both sides of the equation at the stage as powers to which the exponential base 2 will be raised. So applying what we have here. Okay, so I got 2 to the base 2 logarithm of x squared minus 4x plus 3 and that's going to be equal to 2 raised to the third power. Okay, so for what I have on the left, okay, again, the exponential logarithm base 2 will cancel out. Okay, so we have the x squared plus 4x plus 3 is equal to 2 to the third, okay, which is going to be 8. So I have a quadratic equation, and then just rewriting in standard form. Okay, so if I take 8 away from both sides. Okay, so we have that x squared plus 4x minus 5 is equal to 0. And looking at factoring. Okay, so from x squared I have x and x. Then we have factors of negative 5 whose sum or difference will be at positive 4. So we have more weight given to the addition than to the subtraction. And looking at applying the zero product property. So setting each of the factors to 0. Okay, if x plus 5 is 0, x is equal to negative 5. And if we have x minus 1 equal to 0, okay, well, we have that x is equal to 1. Now, looking at what we have for the apparent solutions. And just restating. Okay, so again, we have the original attachments. Okay, have x plus 1 and x plus 3. Again, I said that these must be positive. Okay, so if I were to plug in negative 5 for x, negative 5 plus 1 is negative 4. And guess what? Both attachments had to be positive, and negative 5 already strikes out with the first attempt. Now with 1, okay, we got 1 plus 1 is 2, that is positive. 1 plus 3 is 4, also positive. So 1 is going to check out. So for the second item, there could have been up to 2 solutions. But as it turns out, okay, with the properties of logarithms, there's only one value that will check out, and that is going to be with x equal to 1. Now, for what we have in the case of number 3, again, we have the natural logarithm, the quantity of 2x minus 7 minus the natural logarithm of x is equal to 0. And taking what we have here, okay, so you have logarithmic terms and base e. Okay, and again, so you have a difference of logarithms, and I can put the terms together as a single logarithmic entity. In this case, before I had addition to imply multiplication, and now with the difference of logarithms, we have subtraction to imply division. Okay, and okay, so the attachments, we have 2x minus 7 comes from a positive natural logarithmic term, so this will go to the top, whereas for x, this is attached to a negative natural logarithmic term, so x is going to go on the bottom. Right. And just mentioning, so again, a natural logarithm is going to be a base e logarithm. Okay, so we have for these. Okay, so we have a base e logarithm of 2x minus 7 over x is equal to 0. Okay, and I had jumped out a little bit early, but for what we have for 2x minus 7 over x, okay, this is the attachment, okay, for the single natural logarithmic term. And again, I can take care of the presence of any base logarithm if I take both sides here and apply it as powers to which the natural log base e will be raised. Okay. So for what I have on the left hand side, okay, so we have 2x minus 7 over x. We have the e to the 0, okay, is equal to 1, and setting things up where I can have the x terms presented directly. So if I multiply the equation, by x. Okay, so left hand side will be 2x minus 7. To the right, have 1 times x, which would be x. And gathering the x terms. So I have x by itself on the right. And if I move the 2x over by subtracting, so we'll have that negative 7 is equal to negative x, and changing the signs at both ends, whether through multiplying or dividing by -1. Okay, we're going to have an apparent solution with x equal to 7. Okay, and keeping in mind that the attachments in the equation must be positive. So with x is 7, we got 2 times 7 is 14 minus 7 is 7, which is positive. Again, we have x is 7, also positive. So 7 is going to check out, and that will be the only solution for what we have in the case of this third problem. Now, looking at what we have with, once again, the properties of logarithms. And for what we have for the case in looking at evaluating logarithmic terms, and this is where we have the change of base formula to come in. And for what we have for number 4, we're looking at the base 3 logarithm of 24. Okay, now 24 is a multiple of 3, but it is not an integer power of 3. And if you're looking at approximating, okay, just what that amount will be. Okay, and again, I can use the change of base formula. And we can say that in the case of number 4, so we have for the base 3 logarithm of 24, I can use either natural or base 10 logarithms. Let's go with the base 10 logarithm in this one. So the base 10 log of 24 over the base 10 logarithm of 3, and to about the nearest 3 decimal places. And for the figure I have here, this is going to be about a 2.893. It's about 2.893. Okay, I'll look into number 5. I want to go ahead and skip on over to number 6. In this one case, you have a base 6 logarithm of 216. Now, in a way, you could use the change of base formula, but you can also reduce right away. Okay, because 216 relative to 6 is both a multiple and an integer power of 6. In fact, okay, 216 is going to be 6 raised to the 3rd power. And we can have the exponential and logarithmic bases to cancel each other. And the result is going to be the power to which the exponential base was raised. Okay, so this lowers to 3. Now, in the case of number 5, okay, and you could look at this through either of 2 ways. Well, let me put it this way. You could actually look at it through, I guess, 3 different ways. But here you have the base 5 logarithm of e to the 2nd. And you can use the change of base formula through either using natural or base 10 logarithms. And if you notice, we have with e is in reference to a natural logarithm. And let's say that if we have using natural logs, say the natural logarithm of e squared all over the natural logarithm of 5. Okay, and the follow through could be established in different ways. Let me kind of show you, like a, say if I have like with the calculator approach in terms of how the script will look. Okay, so if I have like the natural logarithm of e to the 2nd, we have divided by the natural logarithm of 5. And we have to about the nearest 3 decimal places. Okay, so this will come out to right at 1.243. Now there is another viable way, okay, in the case of the use of natural logs. Let's see if I can get this to. Or still all over again. Okay, so you had the base 5 logarithm, v squared you can have the natural logarithm of e squared over the natural logarithm of 5. And I just wanted to kind of mention this too. Okay, again, natural logarithm is by definition a base e logarithm. So natural log of e squared is the base e logarithm of e squared base e log of e squared, that will go to 2. If I take 2 divided by the natural logarithm of 5, I'm still going to get the same decimal result. Now, looking at what we have in this case, so there are some of those reduction terms that you can be sort of, I guess what they call it, eclectic with the approaches. Okay, more than one approach to go about following through and reducing. All right, now for what we have in the case of crossing over to what we have with sums and differences of logarithms, as well as combining logarithms. Now we have, starting with the group in number 7, okay, if you notice we have the base 3 logarithm. Okay, we have x squared times a radical divided by a distinct radical term. And we'll say that for number 7, kind of like what I did with the other set where we had radicals. I'm just going to rewrite in terms of non-integer exponents. Okay. So we have here for number 7, we have a base 3 logarithm. Okay, we have x squared, and for the square root of y plus 4, anytime we have the square root of an expression, it'll be that expression to the 1/2 power. And for the 4th root of the cube of z plus 2, again, I can rewrite this where the exponential base is z plus 2, and as a non-integer power, okay, that which is inside the radical will be in the numerator, and the denominator will be what was the index radical number. So after this particular rewrite, okay, I can now write out as sums and differences of logarithms, and where it says to express powers as factors, I'm just converting the raised powers to coefficients. Okay, so for what I have in the case of number 7, now looking at expanding, okay, so I have 2 factors in the numerator, 1 in the denominator, and separating, okay, so anything that is at the top becomes its own positive logarithmic entity. Anything in the denominator translates to a negative term in the logarithmic base 3. Okay, so here we'll have, so if I work with the top attachments, okay, so we've got the base 3 logarithm of x squared, and we have plus the base 3 logarithm of the quantity y plus 4 to the 1/2, and we have minus, okay, the base 3 logarithm, and we have of the quantity, okay, whereupon we have z plus 2 to the 3/4, and again expressing powers as coefficients. So for all three terms, can have conversions from exponent to leading coefficient throughout. Okay, so for the first term, we're going to have 2 times, okay, the base 3 logarithm of x, and we have plus 1/2 of the base 3 logarithm of the quantity of y plus 4, and we'll have minus 3/4 of the base 3 logarithm of the quantity of z plus 2. And for what we have in the case of 8, right, we don't have any radicals, but we have multiple factors involved. And for this one, okay, so we have a base 5 logarithmic term okay, so the base 5 logarithm, okay, so you have 7 and t squared and u to the 3rd at the top. In the denominator we have v to the 5th times z. And looking at taking what we have in this assortment and writing as sums and differences of logarithms, and having the terms where the exponents are converted into coefficients and anything else still in exact form. Okay, so this time we have 3 factors at the top, 2 on the bottom. And if I work with what is at the top first, okay, so the first factor, okay, that is going to be the number 7. So you have a base 5 logarithm of 7, okay, and 7 is not a multiple of 5, and it is not an integer power of 5, so the base 5 logarithm of 7, that is going to remain as it is. And we have next in line, okay, so you have plus the base 5 logarithm of t squared. Then next we have plus the base 5 logarithm of u to the 3rd. Then we have minus, okay, we have the base 5 logarithm and we have the v to the 5th, and then we have minus the base 5 logarithm of z. Okay. All right, so just quick adjustments here with the terms in t, u, and v. And so we have for the final form in this one. Okay, so here we have base 5 logarithm of 7, as well as 2 times, okay, the base 5 logarithm of t, and a positive 3 times the base 5 logarithm of u. Then we have minus, then we have 5 times the base 5 logarithm of v, and once again we have minus the base 5 logarithm of z. So transitioning over from expanding to combining logarithmic terms, and we have with the next 2 items. Okay, so we have for number 9. Okay, so we have expressions in w, x, y, and z. And what we can do, okay, initially, okay, is that for this particular assortment, okay, we can express, okay, the leading coefficients. Okay, so we're shifting gears. Okay, so we're going from expressing powers as coefficients, okay, to where we're going in the opposite direction. Okay, so we have for the case For the leading coefficients, then I can express as powers. And so for what we have in 9, okay, so this is going to become the base 5 logarithm of w to the third. We have minus, okay, the base 5 logarithm of x squared. And we have plus the base 5 logarithm. Okay, we're going to have a y minus 4 raised to the 6th. And we have minus the base 5 logarithm of z to the third. Okay, and looking at putting together as a consolidated base 5 logarithmic term. Okay, so you got w to the third comes from a positive base 5 logarithm, so that goes to the top. X squared originates from a negative, so x squared goes at the bottom. Y minus 4 to the 6th, okay, comes from a positive base 5 logarithm, so that attachment goes in the numerator. And then for z cubed, this comes from a negative base 5 logarithm, so that is going to be on the bottom. And this will be your final result. All right, now for what we have in the case of the next item. Okay, so we're looking at writing once again as a single logarithm. Okay, and tell you what, we'll do this in either two ways to start out. I'll say that for number 10, just kind of repeat the term. Okay, so 2 times the base 3 logarithm of u plus 3 times the base 3 of logarithm of the quantity of v minus 4, and we have minus 3 times the base 3 logarithm. Okay, now with the square root of w to the 4th minus x cubed, I have to write this as a non-integer exponent. Okay, you're going to have the base 3 logarithm, w to the 4th minus x cubed quantity to the 1/2. Again, 1/2 in reference to the square root radical. And looking at ultimately combining as a single logarithm. And I'll just move this over. Okay, so we have in the setup, I can transition what we have with the coefficients, making into exponents. So right now I'm going to have the base 3 logarithm of u to the 2nd. I have plus the base 3 logarithm of v minus 4 raised to the 3rd. And we have minus, okay, the base 3 logarithm. Okay, now we have a bit of a twofold situation. And what I mean by this is where you're going to be looking at the power property of exponents. Now, you got w to the 4th minus x cubed to the 1/2, okay, where we had the original formation from the square root. And then we have with the 3, we're going to have this expression, this difference to the 1/2, and then cubing out right now. No adjustment has to be made to the expressions nu and v. Okay, so u is to the second, v minus 4 is still to the third. And now we have minus the base 3 logarithm. We have a w to the fourth minus x cubed to the 1/2 to the third, so this will be to the 3/2. And now we can put together as a single base 3 logarithm. Okay. So we have u squared, stems from a positive logarithmic term, so that goes to the top. Same thing for v minus 4 raised to the third. And with the last term subtracted, okay, the expression in the variables w and x, okay, will be on the bottom. And this will be your final result, okay, for what we have in problem number 10. All right. Now, going back to equations, and we have with numbers 11 through 13. Okay. And this time we have exponential equations that do not share a common exponential base. All right, so we have for numbers 11 through 13. Okay, so we got 11 and 12 with the variable exponent on one side of the equation. Okay, and for number 11, okay, we have 2 to the x is equal to 3. And again, anytime you have the variable exponent on one side, okay, this is sort of a green light that you can write the equation where we can have the backdrop to utilizing the change of base formula. Okay, so right now we got 2 to the x is equal to 3, and I can go ahead and make the exponent x into just x by itself on the left. So that means I can take care of the exponential base 2 by applying base 2 logarithms on both sides. Okay, so we got the base 2 log of 2 to the x, so this will go to x. And we have that x is equal to the base 2 logarithm of 3. And I can apply the change of base formula. Again, I can either use natural or base 10 logarithms. And we say we had the base 10 logarithm of 3 all over the base 10 logarithm of 2. And for what we're going to have in the case of x, say to about the nearest 3 decimal places, this is going to be right at 1.585. Now, for what we have in the case of number 12, okay, this time we have the equation in terms of the variable e. And for what we have in this one, we have e to the x minus 2 is equal to 14. Okay, so here I can apply, just like what I did with 2, I can knock out the e and have the left-hand side exclusively in terms of the variable x. So I can apply base c logarithms to both terms in the equation. So for left-hand side, okay, this will become x minus 2. And base c logarithm of 14, that's going to be the natural logarithm of 14. And numerically, for the natural log of 14, you have a number that's going to be over 2.6. And looking at isolating x, So if I add 2 to both sides, okay, now we're going to have the x is going to be to the nearest 3 decimal places, right at 4.639. Right. Now, for what we have in the case of 13, okay, now this one, whenever you have the exponent or the variable exponent on both sides of the equation, in terms of the procedures, okay, it can be like a comparative needle to thread. And for 13, okay, so we got 10 to the 3x plus 1 equals 12 raised to the x minus 1 degree. Okay, and okay, so we're looking at the value of x that will belong to both sides. Okay, and for what we have in this problem, okay, so we have 10 to the 3x plus 1 is equal to 12 to the x minus 1 power. Okay, and again, you can apply either natural or base 10 logarithms to both sides. Okay, and since we have since we have 10 at least on one side, okay, it's not going to lead to the change of base formula setup, okay, but it might save you half a step if I use that which matches the base 10. Okay, like if I had e, I might go with natural log just to save maybe half a step. So let's go with log on both sides here. And just to sort of restate, okay, so we got, okay, so anytime we have log, that's going to be making reference to a base 10 logarithm. And so we have with this match, we can say that the left hand side will be at 3x plus 1. Okay, now for what we have to the right, now we don't have a match between the base 10 logarithm and the exponential base 12, but we can still work with the x minus 1 once again by converting as a binomial coefficient where both x and -1 will be multiplying the base 10 logarithm of 12. Okay. Right, so looking at what we have in the follow through. Right, so you got 3x plus 1 is equal to, and for what we have on the right, okay, so we have x times, okay, the base 10 logarithm of 12 minus the base 10 logarithm of 12. Okay, and we have sets of like terms on opposite sides. Okay, and we have the x terms right now to be apart from each other. And I can put those together. So I can just move, let's say, x times the base 10 log of 12. I can also move the 1 over and just have the variable terms on the left, everything else on the right. So for what we're going to have here, okay, so you got 3x minus x times the base 10 logarithm of 12 is equal to the negative of the base 10 logarithm of 12 minus 1. And again, I'm still looking at solving for x. Okay, so what I can do here is that for the difference of terms on the left, okay, I can factor out x. And so we have in the rewrite, okay, so we have x times the quantity, so we have 3 minus the base 10 logarithm of 12 is equal to the difference on the right. Okay, and there are various ways that you can go about following through and getting x by itself if we keep the terms as they are at the moment. Okay, so you have the negative of the base 10 log of 12 minus 1 is going to be divided by 3 minus the base 10 logarithm of 12. And just kind of putting this in terms of calculator inputs. Okay, so you have with the numerator, if you got more than one term in the numerator, you can go ahead and put in parentheses. So we have the negative of the base 10 logarithm of 12 and close out for 12. Then we have minus 1, close out parentheses for the difference in the numerator, and divided by, we have open parenthesis, and you got 3 minus log, and then surrounding parentheses around the constant. Okay, so you have parenthesis around 12 and then close parenthesis for the difference in the denominator. And so you're going to have for x to about the nearest 3 decimal places, and this will be about a negative 1.082. So another sample of what we have with exponential equations, and this time with those that do not share a common exponential base. All right, now reverting to what we have with, once again, systems of equations. And we have with numbers 14 and 15. Okay, 14 we have a linear system, 15 a non-linear. Again, we have with 14 okay, so 2x minus 3y is equal to 7. And the second equation, okay, so you have 4x plus 2y equals 26. And looking at what we have and working with number 14. Okay, all right, so we don't have additive inverses. But we can make an additive inverse set out of what we have in x or y. All right. Okay, so we got 2x minus 3y is equal to 7. And we have 4x plus 2y is equal to 26. Okay, what I can do here is I can cancel out the x terms. And let's say that if I cancel out 4x, what I would need is for the 2x to become negative 4x. So I can adjust the first equation multiplying by negative 2. And for what I have here, it's about negative 2 over the first equation, so we have negative 4x. And negative 2 over negative 3y becomes a positive 6y. We have it's equal to negative 14. And again, I have the second equation fixed. Again, 4x plus 2y is equal to 26. And adding the equations together. So we'll have the x terms to go out, and then we'll have 6y plus 2y, which will be 8y. Negative 14 plus 26 is going to be 12. And dividing by 8. Okay, so yeah, y with 12/8, you say we have y is equal to 3/2, or as a decimal, you can write as 1.5. Whether you write as a fraction or a decimal, in this case, either approach works. Okay, now looking at solving for x, again I can plug in 1.5 for y in either equation. I'll just choose the first one, but it works for the second equation as well. Okay, so just plug in 1.5 for y. So we have 2x minus 3. Okay, and we have, in this particular case, we have 3 times 1.5 is equal to 7. We have 2x minus 4.5 is equal to 7. Okay, so got some decimals in the mix. And for what we have in the case of 2x, okay, so we have that 2x is equal to 11.5, and we have with division by 2, we have another decimal value, and 11.5 divided by 2, we say have 5 3/4 or 5.75. Okay, so for what we have in this system, okay, there's going to be one solution combination for what we have in x and y. Okay, so have x equal to 5.75 and y is equal to 1.5. And again, you can write this as an ordered pair solution, whereupon we have x at 5.75 and y at 1.5. Okay, now just for what we have in the case of the nonlinear system, so here for 16, okay, so you have the sum of squares at 25, and then we have a difference of squares where we have x squared minus y squared is equal to 7. I think I can squeeze this in. Okay, so we have with 15. Okay, so we're looking at x squared plus y squared. It's equal to 25. And again, for the difference, okay, so we'll have additive inverses already established with positive and negative y squared. And what I can do is go ahead and add the equations together. So I have x squared plus x squared becomes 2x squared. And we have 25 plus 7, okay, so that will be 32. And we have a division by 2. So we have the x squared is equal to 16. And we have with the square root property of equality. And go from x squared to x. So we'll have x equal to plus or minus the square root of 16. So we have two possible values of x, which will be the additive inverses 4 and negative 4. And now with this system, again, I have the equations expressed not in x and y, but x squared and y squared. And in terms of solving for y, I can keep 16 for x squared and plug into either of these two equations. And I'll just plug in for the first equation. So plug in 16 for x squared. So I have 16 plus y squared is equal to 25. And we have y squared is equal to 9. And we have, with the square root property of equality, we have that y is equal to plus or minus, okay, the square root of 9. And we have that y is equal to plus or minus 3. So we have for number 15, we have for the solution, okay, so I have two distinct values for both x and y, from which we can have spring forth 4 distinct points. So you can see we have 4, 3, negative 4, 3, also 4, negative 3, and also where both x and y are negative at minus 4 and minus 3 respectively. Okay, and say just kind of rounding out the rest. Okay, we have with numbers 16 and 17. We have the same principal at 3,000, and we have the quoted percentage rate at 6%. Time span will be for 6 years, and the difference will be in the frequencies with the quarterly in number 16 and with the continuous activity in number 17. Okay, so we got for the principal, we got 3,000. Rate we have at 6%. So 0.06. Again, the time span we have for 4 years. Okay, now for 16. Okay, for compounding that is non-continuous, where you had the frequency to run from annual to daily. Got this formula, and filling in. So for P we have $3,000. 1 plus R over N. So R we have at 0.06. N is at 4. And for N times T, okay, so I have 4 times 6. Again, this is from the quarterly compounding. Okay, so I have 3,000. I have times 1.015. To the 24th. Okay, and we are now narrowing it down. Okay, whereupon we have $3,000. And 1.015, okay, to the 24th. And we have, with my figure, have just under 1.43. And with quarterly compounding for this time span, starting out with $3,000, okay, had the future value to be right at 4288.51. And for what we have in the case of the continuous compounding, same starting value, same quoted percentage rate, but the application is where we're going to have continuous, where the parenthetical expression becomes e to the RT. So we have with p times e to the r times t, about 3,000. And for e to the RT, again r, we have a 0.06. T we have at 6. And again, if your calculator does not read the order of operations, we're going to multiply R and T together. So you have $3,000 times e to the 0.36. And for e to the 0.36, okay, this is going to be just over 1.43. And just keeping that decimal, and if you multiply by $3,000, we'll have about as close to $4,300 as you can get and not get there. And for the final balance in this case, we end up at $42.99.99. Okay, so for the same time span, principal, and quoted percentage rate, there's a little difference in the application. With the quarterly compounding, again, you have 42.8851, and with the theoretical maximum, with the continuous, you end up with just a little bit over $11 more at $42.99.99.